the first part of the talk is about the specification part, and then Roy Franz, who's working for Linaro as an assignee from Cavium, is going to talk about a lot of the work that has been going on in the Linaro enterprise group related to the UEFI and ACPI. So the first part of the talk, ideally, would be someone from ARM to talk about this architecture. But I think most of them are from UK, and so they're all happy somewhere else vacationing in August. So I get the honor to represent them. Most of the information actually was done by them, and I just stole the slides and tried to pretend that I understand that. Okay, so quick introduction to UEFI ACPI again, if you missed the first session this morning. And then we talk about the ARM support in both the UEFI 2.4 and ACPI 5.1. And then Roy is going to come up to talk about the Linaro work. Okay, so just to refresh your mind if you were here, but if you're not, this is another chance. So in the UEFI side, we have two parts. The PI, which is the firmware internal interfaces between firmware modules, to make things more modular and modern. And then the UEFI is the interface that you probably care most about in between the operating system and the system firmware. And this is the diagram you would usually see with the green edge as the foundation and the modular pieces to form the interfaces upwards. Okay, so ACPI. ACPI is basically a bunch of tables. Static tables, and provide some of the runtime interfaces to report information upwards to the operating system. So most of these tables are static. It's just tables with information. And the use of it is mostly in three parts, I think. One is for the system configuration. So if you have devices, and in ARM case you do, for those devices that are not on a standard enumerated buses like PCI, right? So a lot of the SoC devices do not have enumerations, and operating system do not have an automatic way of identifying those devices. So ACPI provides a way to describe those devices and the associated properties to the operating system. And power management, right? And thermal management in some cases, as well as the RAS support. So we do have an architecture in ACPI to help the servers to remain operational for reaching the 99.999% of uptime. And the architecture is actually processor architecture neutral. So it doesn't have to be running on x86. That's why we can port it over to ARM very easily. In fact, we ported to some other architectures before as well on Itanium. And I think recently ARM actually published a spec called SBVR, the server-based boot requirement document. It's up there in the ARM.com website, where it specifies the requirements, what kind of ACPI interfaces and also UEFI and SMBIOS interfaces that you need to build into your server platform for ARM64. So one of the tables is kind of interesting, or actually two of those tables, DSDT and SSDT. So those tables sometimes, or most of the time, contain what's called the control methods. The AML, ACPI machine language interpreted code, where you tell the OS what actually needs to be done on the platform, hardware. But you don't do it, I think one of the reasons that why ACPI was created in the first place is not to let the firmware execute the hardware instructions directly, and give the control really to the operating system, and have the operating system provide a sandbox to execute those kind of operations. Firmware is just reporting what the OS needs to do, but the OS actually does it. So if you think about it, ACPI was created at a time. I said it was 1996, right? During that time, what's the predominant power management scheme that was available on PC?
APM.
APM, right? APM was basically code that sits behind SMM, and if it runs out the window, then the OS has no control over, right? So it's kind of a mechanism where the OS vendors wanted to take more control over to the OS side, which the platform vendors at the time didn't quite like. So some of the histories, I don't want to go through all these. It's quite a bit of information. You can certainly look into that afterwards when the slides are made available. But what's interesting to the ARM side is that in 2009, we extended UEFI into ARM ARch32, right, the 32-bit side. And then just last year, we extended that to the 64-bit side of the ARM. And on the ACPI side, the world was more challenging for the ARM SoCs if it were before 2010, because there were a bunch of hardware requirements that you have to be implementing to conform to the spec, right? But fortunately, at the time, Microsoft has already been moving into the Surface RT type of devices, and certainly when they look at the ACPI model, this hardware single point of failure type of implementation doesn't make any sense, right? So that's why you have this hardware reduced ACPI model introduced, and certainly Intel is also doing SoCs these days. So this all works. We all work in the happy family to reduce the hardware requirements. So it's much more flexible for the SoC design. And I mentioned early this morning that last year we also completed the transition for the governance model, where the ACPI used to be owned by 5 companies, and now it's part of the UEFI Forum. So all of us have an opportunity to contribute and revise and making progress forward. So starting from 2014, my point is that with these ACPI and UEFI in one forum now, we do have a very good way of having a common firmware architecture for both x86 and ARM. And so this is another chart of what is part of the UEFI Forum. So who missed this morning's talk? Do I need to repeat this? Okay, so I just briefly talk about, we have a board of directors with 11 members who actually originally started the forum. And then we have quite a number of contributors. I think it's in the 40s or something. I forgot the actual number, but yeah, well, I remember correctly, it's 41. So, and then there's another level called the adopter level. So adopter levels are free to everyone as long as you sign the participation legal agreement. And then the contributors need to pay a little bit to sponsor activities like this and other plugfests and so on. And then we have more than 250, I lost the count, but it's more than 250 members now. And we have multiple working groups, right? So the focus of this talk is going to be on the ACPI side. So ACPI working group was a recent new group that was started this January. So we had about 8 months of operation so far. It's actually the largest group inside of the UEFI Forum right now. A lot of attendees, from ARM, Linux, Windows, and Intel, and AMD, and all that. So it was a very big collaborative environment. Everybody was very constructive in coming up with the new definitions and all that. So on the UEFI 2.4 side, I mentioned that we extended into the ARch64. So here are some of the things that we had to do to make that happen. Basically the P half image that we use to construct the UEFI applications, it needs a number for identifying this is for AR64, right? It's simple. UEFI image file name convention. Well, you had bootx64.EFI. Well, you need a name for ARM64. So not surprising. And the client system architecture is part of the PIXI protocol thing that you need to identify yourself as a ARM64 machine. And then you have some, the calling conventions and structure definitions. I think I have seen a few errata coming up as well. As people start to implement the AR64 platforms, there are a little bit of errata in this space, the register usages and so on. And the 2.4C, in the next few months, will include that. In terms of ACPI 5.1, so the ARM community basically looked at ACPI 5.0 and found that here are a number of things that are missing, right? They missed the information about the gig controller. The ACPI didn't understand the PSCI, the power state coordination interface, if I remember correctly. And then another document that the ARM community did was called the server-based system architecture, which basically defines the minimum hardware dependencies that you can establish for the ARM64 servers for the ease of OS development. And this is called SBSA, and there are different levels, because we tried, ARM really didn't have any baseline before, and we're trying to, make the hardware vendors move toward more standardizations in some of the requirements. So in that document, there are, some of the timer support or watchdog timer support, and those kind of information were not available from ACPI 5.0, right? And there are other things, one of the things the Linux community cared about was some of the keypad values for drivers, right? This is more coming from the device tree type of implementations. So we defined this thing called _DSD, device specific data. So that provides you a way to provide similar kind of a functionality for your operating system. Although, certainly you don't want to just freely do everything you want, because then it's kind of chaotic. So we also have a mechanism or a document that allows you to define your set of information so that everybody else understands. And notice that the other two that they listed up down there, the SMMU IO topology, the gig interrupt translation service, and some of the gig v3, v4 stuff were not yet included, because that's kind of work in progress. You can expect some of these holes being plugged in as we move on, when we have this kind of hardware. And some of the idle management and topology descriptions of what ARM has in mind to create those hardware, those kind of things may come up as well. But the base functions are there, so you could build an ARM server system right now that that use ACPI to describe things to the operating system. I think there was a demo. I think John Masters did earlier this week. Right, it was on the AMD Seattle hardware. So some of the, I quickly go through some of the information here. So I talked about, we missed the information about the gig, right? Gig is now called gig C. Right? So we look at what we had before. This is what Microsoft put in before for the Surface RT kind of devices, for 32-bit ARM. But we need to have more. We need to have V2M. We have to have V3, and in the future V4. So now we have the gig C and gig D structures inside the MADT to describe these interrupt controller information for the ARM systems up to the operating system. right? We already had the other, x86 interrupt controllers there before. Now we have the ARM side. And the PSCI support, so now we have inside of the FADT table, in addition to the i32 boot architecture, we now have the ARM boot architecture bits to indicate whether the PSCI is implemented or not, or whether the PSCI must use the HVC, or whether it can use the SMC. These are all ARM-specific interactions into the PSCI. So using this flag, these couple of flags, the ARM code could be defined to use what's called a fixed function hardware to describe the feature set information to the operating system, and then they can design a driver around it, and the OS can execute that the code, and by interpreting that code, the OS is actually going to call into the PSCI. These are the limited supporting the timer side in 5.0. So now we have a lot more generic timer supports, a lot of structures in the GTDT, which was the table that was in the 5.0 spec already. We just extended that to include the newer timers that ARM defined. And then the watchdog timer as well. So you can kind of get the scheme, right? Anything that's missing, we extended the architecture to accommodate. Not very surprising. So I don't want to dwell too much onto these details. You can look at the slides. You can look at the spec. It's all public now. And I already mentioned the DSD. So the DSD now returns a variable length package of device data descriptor. So it's a UUID and a data structure tuple. So you define your own UUID. UUID is a it's a unique ID, right? I think somebody calculated that by year 3000, you may get a repeat of the number, but who cares, right? ACPI 60.1, maybe you care. Anyways, so there's a document in here that already defined some of the data pairs. So if you have a reason to come up with some additional ones, this is the place to submit and try to document so that everybody knows what you're doing. You don't want it too out of hand, right? I mean, this is kind of could lead to a bit of a messiness, so be careful. And there's another method that was introduced in this version. It's optional, but for some of the system, if the hardware, if the device does not have a hardware-managed cache coherency, you now have a way to describe it. So it's also a tree structures in ACPI. So if the parent device has this property, and you get you get that particular property inherited for the children as well. So some of the ARM devices may present this kind of behavior. So we allow that option to happen. So here's a summary. The draft was, like I said, we had the ASWG started in January, and we have all the all these features included. Publication was there's an IP review cycle because as companies contribute the IP, we need to have a review period, right? So we kind of have a final draft in June, and then we leave people to do IP review and all that. And the publication was July 22nd, and then we did a press release, which is at the table back there on August 12th. So the new key features are already described, and I summarized here. And then the spec is available. So you can go to the website and you just download. There's no form to fill, just download. And here's a quote from the ARM server director. That's part of the press release. So with that, I'm going to pass the microphone to Roy, who is going to talk more on what Linaro has been doing in enabling these platforms through UEFI and ACPI.
Thank you. So I want to talk today on a little bit, introduce the Linaro Enterprise Group, and then sort of review what the current status and what the work we have ahead for ARM servers. So the Linaro Enterprise Group was formed within Linaro in late 2002 to collaborate on and accelerate the development of foundational software for ARM server Linux. So I took that from the website. So I always hate making corporate statements because I just kind of want to say we do stuff and we work together. But that's what we're focused on. And that's grown out of Linaro, which has the more general purpose of bringing together the electronics industry and open source for ARM in general. Started out a couple years earlier, focused more on mobile, and now we have a group within Linaro focused on the enterprise. There's also the Linaro networking group focused on networking. So Linaro's really been growing, and we're an outgrowth of that. So UEFI and ACPI enablement is a key part of what we're working on. So this kind of spans and provides the foundation for many of the things we're working on. So we're working on a number of projects with that. It goes beyond just the EDK2 or the ACPI-CA, which are the main open source projects of UEFI and ACPI respectively. But we're working on Linux, we're working on Grub, we're working on QEMU, we're working on Zen. There's a lot of enablement that spans a lot of different, that touches a lot of different projects. And we're also working on other server projects such as OpenJDK, LampStack, virtualization. So Linaro Enterprise Group is focused on all aspects of that. And we're not the only ones working on it. So ARM, some of the stuff I'm going to be talking about here has been contributed by other people. ARM is, of course, very active at a corporate level, supporting UEFI and ACPI. One of the things I want to emphasize for the enterprise group is that upstream is the goal. This hasn't always been the case in embedded and mobile, where the vendors are shipping products and they have a complete stack and they're going to ship a phone. And open source is good, but upstream isn't required. So that's something that's very different here, is upstream is the goal in all of our activities. It's pushing things upstream. That's where everybody wants to get it. That's what John Masters says all the time and beats his chest about upstream. But I think that's the right way to work. That's the right way to work, and that's really something that's key in the project management that Linaro does is the question is it upstream yet? It's not done until it's upstream. Linaro also provides monthly binary and source releases for the projects we're working on. So you can see what we're working on. We provide builds for you. We provide the source downloads that provide snapshots of work in progress before it is upstream. What are some of the ARM server goals? So we want standard-based servers to facilitate interoperability. That's the key thing that we want to deliver to the end customers. So they want to be able to install multiple Linux distros, or in fact another operating system. The distros want to be able to ship a single kernel that will install on many SoC vendors' chips. And the CD you downloaded 6 months ago should work on the server that you got today. We're not going to be releasing new kernels for every new platform. So basically, it should work like existing servers. So none of these things are really new or shocking. This is kind of how we expect things to work. If you order a system from Dell, all these things are true. So UEFI and ACPI are the key enablers for this. So UEFI provides the common boot architecture. So that's what people are used to. That's widely deployed. That's widely used. And ACPI provides a stable hardware description. So one of the things stable over time is one of the key pieces of this. So in order to support a distro that's installable on multiple machines, on machines that haven't been built yet, we need a hardware description that's stable over time. And as Dawn has talked about, there's now a defined process for change. So ACPI is much more available for change and improvement and involvement by the community than it used to be. So both of these things are new for ARM platforms. So if you wanted to run a Red Hat installer on an ARM platform a couple of years ago, would be hard to do. That would be hard to install in anything. You know, there would be an occasional ARM platform that somebody had custom done a Debian installer for, and it would work for a little while. ARM servers also have no legacy. There's none of, this is how we've done it, so we're going to do it that way again. We don't have a lot to fall back on. So we have to use this freedom wisely, because we really want to meet our end users' requirements. We want them to be able to work with the servers. So I'm going to move on to talk about sort of what's been done and what we're currently working on and where we're going. So we have the EDK2 running on a variety of supported platforms. I'll talk more about those in a little more detail. We have the Linux EFI loader and runtime services implemented for ARM64 and ARM32. That's already been merged upstream for ARM64. It's expected soon for ARM32. So what this is, this enables Linux to be an EFI application. So rather than having uboot or grub specifically know the payload that it's loading, as it does, you know, a pre-EFI loader. So grub would know, I'm loading an ARM32Z image, I need to load it at these addresses, I need to branch to this offset from the beginning of it. That all goes away, and now you can, the Linux kernels themselves will be an EFI application. So you can start it, EFI shell, get your EFI shell, and execute the Linux kernel as an EFI application. And the EFI loader that is integrated with the kernel knows how to load the kernel. It knows how all of that boot protocol, and then starts the kernel. So this allows grub to, instead of knowing how to deal with all of these different boot protocols, it simply loads the Linux kernel as an EFI loader. So we've also added to this also includes the runtime service. So very, very shortly, both ARM32 and ARM64 will be very similar in that regard and have runtime services and boot support. We've also extended ARM64 grub so that supports EFI, so it also is an EFI application, and then will load, chain load the Linux kernel as an EFI application. The other thing is FDT for non-ACPI systems. So not all ARM systems are going to be ACPI. You can do UEFI without ACPI, and in fact, that's the state for all the 32-bit systems. So moving on to the completed ACPI work. So we have the ACPI CA support for the new tables in 5.1. So that's been released. The ACPI CA is the open source upstream for the ACPI utilities. So these are the A&L compiler and the tools to compile those tables. So that's also a source base that's merged into the Linux kernel on a regular basis. So Linux kernel support on ARM64 for these new ACPI 5.1 tables is expected in kernel 3.18. And in Linaro, we've also integrated several of the test suites into our Lava system. That's the Linaro automated validation environment. So this is a continuous integration and automated test system that we run on hardware and software platforms. So we have a number of the test suites that were talked about. The Canonical's firmware test suite, so the ACPI sections of that are being run currently, as well as some other ACPI test tools in that test environment. So testing is very important. You want to catch these bugs before things ship. The supported platforms, we have a variety here. At the top of the list is the ARM Juno evaluation board. So this is ARM 64-bit evaluation platform. It has multiple A57 and A53 cores. So that is very close to booting in an ACPI-only setup. So did that get done? I didn't check with the. Last I checked, it was very, very close. So that's an example of something that's booting ACPI only. So ACPI, while we're talking about it, and that's where we want to go, this is very new. So this was when I wrote these slides, 2 weeks ago. It was close. So this is stuff that's happening right now. So a lot of this stuff is very much in process, or very active development. ARM also provides their foundation, their FVP and foundation models. So these are software-based development platforms. These emulate the hardware platforms. We do a lot of development in those, and the foundation models are free of charge to download. So I think there's a registration process, but those are available if you would like to work with ARM64, an ARM64 platform. There's the Applied Micro Mustang board, which support is in progress for.
That's done as well.
That's done as well? Okay. So some of the stuff is happening so fast, it's hard to keep track of where everything is. So we also have a number of non-ACPI platforms. There's the Huawei D01, which is a 16-core A15 server. So that is UEFI and device tree. The older 32-bit ARM vExpress are supported on UEFI, as well as the QEMU vExpress system model. So that the QEMU model is the most open. So if you wanted to play around with UEFI and ARM, it's 32-bit, but that is something that's all freely available. So QEMU from its sites, and you can download the source code for that from the Linaro site. Sorry, the source code for UEFI for that from the Linaro site.
Seattle's done as well.
Sorry, yeah, I somehow have missed that. So this is really starting to sort of hit the tipping point and be moving forward quite quickly. So active work that's ongoing now. Zen, ARM64, UEFI and ACPI support. So the same thing that was done for Linux, make it a UEFI application, add runtime services. There's a lot of continuing work on the specification. So the ACPI specification working group to finish the ARM64 support and then finish the implementation of that as well. Grub support for Zen, some additional networking support. We've been working on secure boot as well, so making sure the signing tools work, that we can sign a kernel, that all works. As well as we're having a lot of discussions of UEFI as a virtual machine firmware and getting that to run in a virtual machine. This provides a lot of opportunities for standardized virtual machine disk formats and boot procedures for virtual machines as well. Next steps, a lot of ongoing work on the specification. So that's still, very much a lot of active work going on there. Also, UEFI secure variable storage. So part of secure boot is you need a secure space to put your certificates and such. On x86, that might have done it in a TPM or similar hardware. ARM has trust zone, and it's secure execution mode. So we're talking about how we can standardize storage of those, leveraging some of the unique features of the ARM architecture. And continued UEFI test coverage improvement. So some of the test suites that were described in an earlier talk here, there are ongoing discussions of how to integrate more and more of those into Lava, so that as we bring platforms up, that they will be continuously tested, and that we can really work to maintain high firmware quality. So a few points on ongoing UEFI enablement. So we really want to encourage the Linaro collaboration on platforms and drivers. Right now, the main EDK2 repository is primarily core architecture code and a couple of evaluation boards. So we really want to provide a place for platforms and drivers to come together. So we're collecting those in the Linaro tree right now, but we really want to work to have an upstream where all of this code can go. So right now, for instance, the QEMU UEFI port, that's the Linaro tree, because there is no upstream that really is taking that right now. So, but that's something that we're continuing to work on, as well as UEFI beyond servers. That's really where a lot of the interest is, where there's a customer demand. This is really clear that UEFI and ACPI for servers is what's needed right now. All of the work we've been doing it's fairly architecture agnostic, so a lot of it works for ARM32 and ARM64. So we've sponsored a Google Summer of Code project to get UEFI running on the BeagleBone Black. If you're not familiar with that, it's a very small, inexpensive ARM32 board. So that is close to being done, as well as supporting Android on UEFI. So this involves porting the fast boot protocol. This is a protocol that Android uses to burn the flash and other things, so that enables Android to boot on UEFI. So both of those, again, would be using device tree, not ACPI, so there's no real hard linkage there. And UEFI beyond servers is really something that's going to be on an as-needed basis. I mean, we're hoping that this will be a great success in servers, and that based on seeing it being done, seeing it working, that this will expand. But there's certainly no mandate for UEFI in the embedded space. And I have a These slides are available for download. I have a few reference slides here. It's just of the Linaro mailing lists. The work is really done in the open there, so we have open mailing lists, open repositories. So we have some ACPI and UEFI stuff there, as well as where you can get the downloads of our monthly builds. And that's what I have. Do we have any questions?
So the idea here then will be to replace the device tree for configuring your hardware?
For servers. So I want to just emphasize that this is, this talk was building ARM servers.
Okay.
So UEFI and ACPI, yes, are the plan for
so like
ARM servers.
ARM SOC vendors, one of which I happen to be employed by, are going to have basically a massive porting effort for all their drivers that are now in the device tree, and all these device tree bindings that are going in are going to be obsolete. Is that?
Absolutely not. No, we're being very sure about that. That if you are trying to do something if you're trying to get into enterprise, this is the market requirement. Just the way that the market's set up, standardization is key. It's very important. If you want to be in that market, you have to do ACPI.
Yeah, I agree.
For embedded, there isn't the same driver. I mean, you've got a vertical stack. The one vendor's got control of every part of the stack. Device tree has a different design philosophy. ACPI has an abstraction layer where you have a certain amount belongs to the platform. If you've got a system where you own everything, it is, and we've got all the facilities in the kernel, we want that in the kernel device tree exposes all that data to the kernel, so the kernel can make the decisions. It depends on the market you're going for. And really, when we're talking about the ARM world, we've got the whole ARM ecosystem, and we've got enterprise, which, in terms of development activity, is very small compared to all the other stuff that's going on. Incredibly important, but they are different, and we're not going to have a mass migration.
They're different SOCs too. So like you're not taking the same SOC and saying, this SOC suddenly I've got to do the same driver work twice. It's like they're different devices and different chips, and I don't think, I'm not trying to say anything that's not public, but I don't think anyone's going to say, hey, I've got this embedded chip and I'm going to put it in. That's not what's happening.
There's also things that what we've learned when we've been going through this stuff is, building on what John just said, the parts that are, when we start looking at ACPI, especially as it exists now, makes a whole bunch of assumptions about what your hardware is going to look like. Right? It's got some assumptions that ACPI and firmware are going to be able to do your clock management and all of those things because the SoC has been designed in such a way to make that practical. You may be able to do horrible things to make it work, but you really don't want it. The embedded CPU, the embedded platforms have all kinds of crazy stuff all over them that you're not going to see on a general purpose machine. Now, if we're going to take a look at 5 years down the road, is the market going to look something different? There will probably be some change. When we have a nice, really solid ecosystem, we prove this all work with ACPI and UEFI on the enterprise market space, you're going to start to see some bleed out into other markets. But I still do not think that we're going to have a massive migration of all DT to ACPI.
And I think that bleed out is probably going to be more UEFI than ACPI.
UEFI will be first, because UEFI it's easier to come up with, it's easier to say why UEFI is advantageous over the incumbent solution on embedded.
Well, I think this is going to be, I think this is really making it important. This is, if this moves, this is going to be a pull model. It's not going to be a push model. Nobody's going to be pushing, you must do UEFI, you must do ACPI on your mobile SOC. But you might say, hey, UEFI is working great, and we don't want to do this other bootloader. We'll just have our little boot firmware start UEFI, and then get all this other stuff. And we could install that, and we could maybe install Red Hat, or we could install something else, and you could just have the installer work. I mean, I think that if that is working in the enterprise space, and it's really the only thing that would keep Red Hat from being installable on a phone with UEFI once it has 64-bit ARM, which is going to be there, is device tree versus ACPI. So you get a distribution that says, hey, we support booting a kernel with device tree. Boom, you could now do a network install on your phone And that could be, without ACPI, that could be a compelling reason for why mobile wants to move to UEFI. But that's a totally separate issue from device tree versus ACPI.
ACPI costs money too, right? ACPI isn't free. Like, there's no reason. I mean, you know, I'm a huge ACPI fanboy, right? But I'm the first person to say it costs you money to do ACPI because it makes these assumptions that are going to cost you money. If you're a mobile guy, you don't want to do that.
Sorry.
I'm going to reiterate a question I actually asked you yesterday. Given this talk is about ARM servers, and we're saying ARM servers are going to have this UEFI plus ACPI, are you going to be able to call something an ARM server without, say, either of those two?
Well, I don't know that there is a ARM server. I don't think is a registered trademark with the standards body to enforce that. So I think this is more of that if you have an ARM server and Red Hat Enterprise Linux won't run on it, and you can't run the OS vendors installers, I don't know. I think that that's where you're going to run into the problem of calling it an ARM server.
No, but we've got documents, right?
Yeah.
We've got ways that these things can be described in concrete terms. For example, there's 2 documents that are published by ARM that describe the hardware, the requirements on hardware for enterprise machines and the requirements on the firmware. And so John will tell you what Red Hat will require to support RHEL on a piece of hardware.
So that's going to be the SBSA and what the SBR are.
Then there's no support. So you might be able to get it to run, but that's not the same as support.
Okay.
Is the standardization going to make it difficult for vendors to differentiate their products?
I don't think so, because this is talking about how you figure out what device you should boot from, or how you specify boot from USB or network boot. So I don't think that there's much interest in differentiating there. And I'm coming from an SoC vendor. I mean, this hasn't come up as, oh my gosh, this is going to affect our differentiation. So that hasn't come up internally at all.
I was just interested in the fact that you're hiding quite a lot of information under the ACPI thing. You're saying we're going to make it very much simpler, say clock model or other models.
But this is talking about, so if we have some super fancy widget that makes Hadoop 10 times faster, we just need to describe where that is, so that when the driver that we've given you loads, it says, oh, I have this here, here's my base address, and here's my that doesn't affect how we do DMAs or memory mapping or register accesses or data flow or anything. So that's some driver we load later. So I don't think that really affects it, because basically the way these things exist now in SoCs is they're at some fixed address, and we just need a simple way to here's where they are in the memory map, here's what's there, and so I don't see that really affecting that kind of stuff at all.
I can also add, I think I mentioned the UUID in the earlier talk, right? So one of the things that you can think about UUID is unique. Well, I said it's, before EX 3400, it's unique. So with that feature, one of the, if you look at UEFI, right? UEFI has a lot of protocols for boot services, and you can define your own protocols. We at HP, I think initially, we have a legacy of supporting tape drives. We still do in some of our systems today. And the general mass doesn't have that need. Well, it doesn't matter. We created our own UUID for a protocol, which is called tape.io. If you don't care, you don't have to use it. But some of the other segments care, so you create your own protocols for that.
Punch cards.
Yeah. And ACPI has the same UUID concept now as well. So yeah.
And the other thing that with ACPI is that just because that's what the firmware does, for a particular, if you're taking an off-the-shelf server and you want to do something funky with it and really have control over things, ACPI is data provided to the kernel. The kernel always has the option to just ignore everything that firmware tells it. It's got more work to do to now figure out how to run that hardware, and if you've got hardware specs, you can do that. But ACPI defines a power model that you can program to, which is convenient, and it's good for an ecosystem.